Hello, ladies and gentlemen, boys and girls, and friends beyond the binary. Welcome to Cosmic Cradle. This is your host, Felix, and today we're gonna talk about the sun. Before we do that, though, there's some explaining to do. Since this is my very first episode, my very first podcast, in fact, I need to tell you what you can expect and what I want to do with the show. Now, those who are familiar with sleeping podcasts would know that the intro here was more or less stolen from Scooter from Sleep With Me podcast. And a big shout out to Scooter because that guy has helped me fall asleep oh so many times. I've actually lost count. Now, for those who are unfamiliar with sleeping podcasts, what they're meant to do is to basically bore you to sleep and give you some background noise if you're tossing, turning, mind racing, can't really fall asleep. Then you got me here in the background, just gonna talk about space and the stars and the universe and everything in it. And if you notice me going off on tangents, don't worry, that's part of the formula for the sleeping podcasts. It's meant to make your brain drift away and not really focus on any thoughts or anything that you can't really affect now, so just to make you fall asleep. Now, if it doesn't work for you with my voice, then I highly recommend you check out Scooter's podcast, Sleep With Me, at sleepwithmepodcast.com, because he's really good at what he does, and I'm doing this for the very first time, so I completely understand if this doesn't work, so I'll leave some links in the description to some episodes, and hopefully you will fall asleep shortly. And now if you decided to stay, let's get on with the show. I currently do not have an intro, so I'm just gonna start. And like I said in the beginning of the episode, I wanted to talk about the sun. And as we know, the sun is our closest star, is our host star, in fact. Our planet orbits around it, unlike what our ancestors used to think, because they thought it revolved around the Earth. And if you're standing on the Earth and you're looking up, it really looks like it's going around, because you see it going up in the east, and then it goes up in the sky, and then it settles in the west. And as some people say today, the Earth looks really flat. So imagine a world without internet or really much knowledge, then it would be a very reasonable conclusion to make. And not to dismiss all of our ancestors, they were just as intelligent as we are, but just equipped with less facts and less observations of the natural world. Now, we did have some ancient philosophers and ancient observers, if you may, that did notice peculiar things about the sky. And while we're talking about flat Earths, there was this person called Eratosthenes, who lived around the 3rd century BC, or BCE as we say today. And he actually measured the circumference of the Earth with astonishing accuracy, especially for the time. That's more than 2,000 years ago. And the way he did it is actually quite remarkable. He did it without leaving his home city of Alexandria. He just relied on knowledge that I suppose he got from travelers or emissaries or whatever it might have been. But he knew that at local noon on the summer solstice in a city called Syene in Egypt, the sun was directly overhead. And he knew it was directly overhead because the shadow of someone looking down a deep well at the summer solstice at local noon in Syene would block the reflection of the sun in the water. And he measured the sun's angle of elevation at noon in Alexandria by using a vertical rod known as a gnomon, and measuring the length of its shadow on the ground. And using the length of the rod and the length of the shadow as the legs of a triangle, he calculated the angle of the sun's rays. Combining this with how far it was to Cyan from Alexandria, he managed to calculate the circumference of the Earth, being only wrong by 0.16%. That is almost a fifth of a percent, which is really amazing if you think about the fact that it was 2,000 years ago. So people have known that the Earth was round or an oblate spheroid. Well, they didn't know that it was an oblate spheroid, which is basically just a deformed pear-shaped sphere. They figured that the Earth was round, and with their measurements it was round enough to be perfectly round. And yeah, the notion of a flat Earth is actually a modern phenomena, because the so-called flat Earth theory has very many conspiracy elements in it, like the fact that the Earth's circle or the Earth plane is surrounded by a giant ice sheet that is guarded by NASA. And NASA didn't come into existence until the 1950s, so who guarded the ice sheets before them? And now I'm sure that they have perfectly reasonable answers to who that might have been, or why there was no need to explore Antarctica, or the technology didn't exist. But I digress. I'm not here to debunk the flat Earth theory. I'm here to talk about the sun, which is the closest star to the Earth, like I said earlier. But it actually isn't that close. It takes light 8 minutes and 19 seconds to travel from the surface of the sun and to hit our retinas here at Earth. But that time varies a little bit, of course, because the distance isn't constant. We're not in a perfectly circular orbit. It's slightly elliptical, so around 8 minutes and 19 seconds, which at light speed, which is 300 million meters per second, which would be 984 million feet per second for our imperial listeners. And that would land the sun about 150 million kilometers away from us, or 93 million miles. And that's quite a fair distance. We do define that distance actually as an astronomical unit. So the Earth is 1 astronomical unit away from the sun. And the sun has been sitting there. Well, it hasn't actually been sitting there. It's actually moving in the galactic disk in its own orbit around the center of our galaxy, which contains a black hole. But I think I will leave that for another episode. Now the sun has been in its orbit for about 4.5 billion years. That's a billion with a B, which is 1,000 millions. So it's quite old. But that, of course, is in comparison to a human lifespan. Compared to its own lifespan, it has reached middle age. It has about 5 billion years left, so it's in the lower part of its middle age, and compared to the universe, it's about 3 times as young. The universe is supposedly to have come into existence about 13.7 billion years ago. And the sun formed from stellar dusts that had come from giant explosions of other stars called supernovas, which happens when very massive stars reaches the end of their lifespan. And it happens because the star is unable to sustain the nuclear fusion reaction where they press together atoms and they join together to form new atoms and release a lot of energy to withstand the gravitational pressure which comes from the fact that they are very, very massive. And this happens, of course, only to the massive stars because the energy required or stored in the atoms that are formed demands even higher energies so they can form more new elements. And the most heavy element a star through gravitation can fuse is iron, and there's barely any iron in our sun. There is some, but for these massive stars, there's a lot of iron, so it gets very, very, very heavy, and they explode, and it gets even more energetic and even more hotter, and even newer substances can form in such explosions. And it was such explosions that formed the elements that formed our solar system, and it might probably be those elements that we can find the traces of in our sun. I doubt there is some iron formed by the sun in the sun. No, our sun is mostly comprised of hydrogen. In the most part, almost 3/4 of the sun is hydrogen, and a quarter is, or a little less than a quarter, is helium, and then you get traces of oxygen, carbon, iron, neon, nitrogen, silicon, magnesium, and sulfur in that last percent. And of course the amount of helium, which is the element next in the periodic table after hydrogen, which is the most simple atom containing only one proton and one neutron, which, well, it's the proton content that defines what element it is, but together they have two protons, and if they share a core, that atom is now called helium, which is what we're talking about. And when the sun is mostly helium and it has burnt or fused all of its hydrogen, it will exit its so-called main sequence, which it is currently in, and start to turn into a red giant. And it will indeed be giant. We mentioned earlier the astronomical unit, and that's the distance from the Earth to the Sun, and it will be expanding to a diameter of 2 astronomical units, which is to say a radius of 1 astronomical unit, which is to say it will knock on our back door and boil most of the planets. And it will continue to expand and pulsate until the core of the sun, which will be exposed, and that core is then called a white dwarf, which will have a temperature of 100,000 Kelvin, which would be 100,273 degrees Celsius, and containing about 50% of the sun's present-day mass. And the outer shell that was the red giant part, I guess, would fall and collapse into a so-called planetary nebula, which will disperse in about 10,000 years. But the dwarf, the core, it will survive for trillions of years before fading to a so-called hypothetical black dwarf. Since in a white dwarf no fusion occurs, that is what caused the red giant phase in the first place. Now, a black dwarf is very theoretical because the amount of time for a star to achieve such a state is much greater than the actual age we've calculated for the universe. Remember, it was 13.7 or around 14 billion years compared to a trillion years, which is 1,000 billions. And so we've barely reached 1% of such a time span. So we don't have to worry about that now. It's quite far in the future. So in the present, the sun is still active in its main sequence. It's still sustaining nuclear fusion, and which we are reaping the fruits of its labor from by the light that it's emitted from the star that transports energy to the earth, and which gets absorbed by the plants, which we then consume. So we have a lot to thank our little sun for. And where is this fusion occurring? Is it occurring all over the sun, or is it just occurring inside the core? It's actually just inside the core, because that's where the gravitational pressure is the greatest, and the core is about 0.2 to 0.25% of the solar radius, which is from the middle to the surface, and that is quite small in comparison. But if you would compare that to the size of the Earth, it would be about 20 to 30 times its size. So it's still comparatively bigger to, if you compared it to the size scales that we're used to in our everyday lives. Now, the core of the sun is the hottest part of the sun. It's also very dense due to the gravitational pressure. It's about 150 times the density of liquid water at the center, and it's about 15 million kelvins, and that's high enough to be the same in Celsius. The 270 degrees difference is negligible. And you've also got, for our imperial listeners, it's about 20 million degrees Fahrenheit. So the core is very hot, and it's made of a plasma, a dense plasma, which are ions, that is atoms, which has been stripped of some electrons, or has gotten some extra electrons, and the pressure is about 265 billion bar, which is 1 bar is 1 atmospheric pressure. So a place that is 265 billion times that pressure, it's not surprising that strange things starts to happen. And I will leave what actually happens inside the core and such until I've advanced further in my academic career, because currently I am certainly not adept enough to explain why. So there are, of course, other topics about the sun we can discuss, such as its English name, the English proper name, sun, developed from Old English, Sonne, and may be related to south. Cognates to English sun appear in other Germanic languages, including Old Frisian, Sonne, Sonne, and Old Saxon is Sonna, and you get Middle Dutch, Zanne, or Sonne, and the modern Dutch is Zon. You got the Old High German, Sunna. No, that sounded Finnish. Zunna. And you got the modern German, Zonna. And the Old Norse, Zunna. And the Gothic, Sunne. All Germanic terms for the sun stem from the Proto-Germanic Sunnon. The Latin name for the sun, soul, is not commonly used in everyday English, although here in Sweden we call the sun soul. Soul is also used by planetary astronomers to refer to the duration of a solar day on another planet, such as Mars, but it might as well be Venus or Jupiter. But here on Earth, we just call it a day. And now, not only does the sun play a big role in the existence of life on the Earth, it has also played a humongous role in human culture, in our history. Many deities has been represented by the sun, and it's highly understandable because the sun is you can feel its effect when you see it, and when it's gone you don't. And for our ancestors it wasn't a guarantee that it would show up every day. So every new day will be a cause for praise because the sun decided to show up and enrich us with its energy. And in turn, according to the Egyptians, and of course it is still true, that it will give life by that energy, controlling the ripening of the crops which were worked by man. And because of the life-giving qualities of the sun, the Egyptians worshipped the sun as a god. And of course, it wasn't just the Egyptians who considered the sun to be gods or deities of some sorts. You got farther down the African continent, the Tiv people who considered the sun to be the sun, the male child of a supreme being, a Wando, and the moon would be a Wando's daughter. So the sun and the moon there would be siblings, which actually isn't too far from reality. In fact, the entire solar systems, all the bodies in it, could be considered siblings because they weren't created necessarily by the sun or something. They formed by the same planetary and stellar dust that was here before we were here, and most of the things in the solar system were formed at the same time. Taking different amount of times, of course, to mature or to achieve the form and the location they have today. Now, the solar deities aren't always male. They usually are, though, and the lunar deities are thought of as females. But in Germanic mythology, the sun is female and the moon is male. The old High German sun goddess is Sunna, and in the Norse traditions, Sol rode through the sky on her chariot every day, pulled by two horses named Arvak and Olsid. Sol also was called Sunna and Frau Sunne. And other cultures that have sun goddesses include the Lithuanians, the Latvians, the Finns, and the Hungarians. And the earliest understanding of the sun was that of a disk in the sky whose presence above the horizon creates day and whose absence causes night. In the Bronze Age, this understanding was modified by assuming that the sun is transported across the sky in a boat or a chariot and transported back to the place of sunrise during the night, passing through the underworld. Many ancient monuments were constructed with the passing of the solar year in mind. For example, stone megaliths accurately mark the summer or winter solstice. Some of the most prominent megaliths are the Nabta Playa in Egypt, Menadra, Maita, and at Stonehenge in England. Newgrange, a prehistoric human-built monument in Ireland, was designed to detect the winter solstice. And you've got the Pyramid of El Castillo at Chichen Itza in Mexico. That was designed to cast shadows in the shape of serpents climbing the pyramid at the vernal and autumnal equinoxes. And you still have religions today, such as Hinduism, where the sun is still considered a god. One of the first people to offer a scientific or philosophical explanation for the sun was the Greek philosopher Anaxagoras. He reasoned that it was not the chariot of Helios, Helios meaning sun in Greek, but instead a giant flaming ball of metal, much larger than the land of Peloponnesus, and the moon reflected the light of the sun, which was not thought of for a long time. Even today, some people think that the moon emits its own light. And when Anaxagoras tried to teach this newfound information, he was imprisoned by the authorities and sentenced to death, a very common trait among ancient astronomers. Though he wasn't executed, fortunately, he was later released through the intervention of a person called Pericles, assuming a friend maybe. And later on, the theory that the sun is the center around which the planet's orbit was first proposed by the ancient Greek. Of course, it's a Greek, Aristarchus of Samos, in the 3rd century BC, together with, or at the same time, it's Eratosthenes. So, and I see some connections here, and this view was developed in a more detailed mathematical model of a heliocentric system in the 16th century. So, 19 centuries later, by the well-known Nicholas Copernicus. Now there wasn't just Europeans who looked up at the sky. You've got some Arabic astronomical contributions, include the Albatenius discovery that the direction of the sun's apogee, the place in the sun's orbit against the fixed stars where it seems to be moving slowest, is changing. In modern heliocentric terms, this is caused by a gradual motion of the aphelion of the Earth's orbit. Ibn Yus observed more than 10,000 entries for the sun's position for many years using a large astrolabe. And an astrolabe is an old tool for navigators and astronomers that they use to measure the altitude above the horizon of a celestial body, day or night. And it looks almost like a clock, but instead of arms, it's got circles inside, and there's a machinery that ticks them around, showing where things should be at which time. So it's a very mechanical device and very impressive. Our ancestors were really smart. And one of the smartest ones, Sir Isaac Newton, in 1666, observed the sun's light using a prism, and he showed that it was made of light of many colors. When the light shone through the glass prism, he went inside a shed and completely enclosed it and opened just a little slit on the wall to allow some light to pass through, and for him to control just a single light beam. And when he placed it in a prism, which he bought at a market, actually, it was just a fun toy, but when he put this in this controlled environment, he saw that the colors of the rainbow appeared on the other side of the prism. And even more astonishing, he got the idea to take a second prism and put it on the rainbow colors, and he found that they merged together and formed a regular light beam again. And he proved that the sun's light was made up of all the colors. So despite what we learned as kids in kindergarten. When you mix all the colors, you get a very dark black color. That's not true for light waves. When you mix light color all together, you get white. Of course, the sun's light is made up of more than just the colors of the rainbow. That's just part of the so-called visible spectrum that we as humans can detect, which is the abilities we've inherited from billions of years of evolution. So it's quite good that we don't see the other light waves, because then our vision would be very, very, very cluttered. And this was discovered about 150 years later, after Isaac Newton discovered the composition of light. In 1800, William Herschel, he discovered infrared radiation by using the same method as Newton to divide light, and his intention was to measure the temperature of of each color of the light. So he separated the colors using a prism like Newton, and placed a thermometer on each color, and he before the red, just next to it, he wanted to have a control thermometer to see what the temperature of the room was. And it was lucky that he did not put it in another completely other area of the room, which seems to be more scientific. Or maybe he did, and people forgot about that. But the one that was next to the red color was much hotter than the room and the other colors, and that was the first suggestion of light that we can't see. And it took a long time until we actually figured out what the sun was. Many suggestions, from a burning lump of coal to hot disks being pulled by chariots. It was not until 1904 when a documented solution was offered. Ernest Rutherford suggested that the sun's output could be maintained by an internal source of heat, and suggested radioactive decay as the source. However, it would be until Albert Einstein who would provide the essential clue to the source of the sun's energy output with his mass-energy equivalence relation that we know, E equals mc squared. In 1920, Sir Arthur Eddington proposed that the pressures and temperatures at the core of the sun could produce a nuclear fusion reaction that merged hydrogen into helium nuclei, which we talked about. The preponderance of hydrogen in the sun was confirmed in 1925 by Cecilia Payne, using the ionization theory developed by Meghnad Saha, an Indian physicist. The theoretical concept of fusion was developed in the 1930s by astrophysicists Subramanian Chandrasekhar and Hans Bethe. Hans Bethe calculated the details of the two main energy-producing nuclear reactions that powered the sun. In 1957, Margaret Burbridge, Geoffrey Burbridge, William Fowler, and Fred Hoyle showed that most of the elements in the universe have been synthesized by nuclear reactions inside stars, some like the sun, and that in the beginning most of everything was just hydrogen, or maybe lithium, or only the lightest elements, the heaviest, were so-called synthesized by the inhabitants of the universe, the stars. Now in the modern era, we've been able to do more than just look at the sun's light rays as it hits the earth. We've been able to send machines over there and The first satellites designed for long-term observation of the Sun from interplanetary space were NASA's Pioneer 6, 7, 8, and 9, which were launched between 1959 and 1968. These probes orbited the Sun at a distance similar to that of Earth, and made the first detailed measurements of the solar wind and the solar magnetic field. And the reason is it's very hard to send things to the Sun, because we're already going around it at a very fast velocity, and in order to get closer we need to work against that speed, and there's still benefits to be outside Earth atmosphere, because the atmosphere scatters the light and absorbs it and makes all these kind of distortions in our measurements. So even having them close here in the same orbital plane, we can still obtain very useful information. And of the Pioneer probes, Pioneer 9 operated for a particularly long time. Being launched in 1968, it transmitted data until May of 1983, so that was almost 15 years. In the 1970s, two Helios spacecraft and the Skylab Apollo telescope mount provided scientists with significant new data on solar wind and the solar corona. The Helios 1 and 2 probes were US-German collaborations that studied the solar wind from an orbit carrying the spacecraft inside Mercury's orbit at perihelion, which is its closest approach to the star, the Sun. The Skylab space station, launched by NASA in 1973, included a solar observatory module called the Apollo Telescope Mount that was operated by astronaut residents on the station. Skylab made the first time-resolved observations of the solar transition region and of the ultraviolet emissions from the solar corona. Discoveries included the first observations of coronal mass ejections, then called coronal transients, and of coronal holes, now known to be intimately associated with the solar wind. A coronal mass ejection, by the way, is a significant release of plasma and accompanying magnetic field from the solar corona. They often follow solar flares and are normally present during a solar prominence eruption, which look like big storms leaving the surface of the Sun, but coming back often in a loop shape on the Sun's surface. Prominences are anchored to the Sun's surface in the photosphere and extend to the Sun's corona. In 1980, the Solar Maximum mission was launched by NASA. This spacecraft was designed to observe gamma rays and X-rays and UV radiation, the part of the light that we can't see coming from the solar flares during a time of high solar activity and solar luminosity. And just a few months after launch, however, an electronics failure caused the probe to go into standby mode, and it spent the next 3 years in this inactive state. In 1984, Space Shuttle Challenger missions STS-41C retrieved the satellite and repaired its electronics before re-releasing it into orbit, and the Solar Maxima mission subsequently acquired thousands of images of the solar corona before re-entering the Earth's atmosphere in June of 1986. And launched in 1991, Japan's Yooko Sunbeam satellite observed solar flares at X-ray wavelengths. Mission data allowed scientists to identify several different types of flares and demonstrated that the corona away from regions of peak activity was much more dynamic and active than had previously been supposed. Yoko observed an entire solar cycle, but went into standby mode when an annular eclipse in 2001 caused it to lose its lock on the sun. It was destroyed by atmospheric re-entry in 2005. One of the most important solar missions to date has been the Solar and the Heliospheric Observatory, jointly built by the European Space Agency and NASA and launched on the 2nd of December 1995. Originally intended to serve as a 2-year mission, a mission extension through 2012 was approved in October 2009. It has proven so useful that a follow-on mission, the Solar Dynamics Observatory, was launched in February 2010. Situated at the Lagrangian point between Earth and the Sun, at which the gravitational pull from both is equal, SOHO, or Solar and Heliospheric Observatory, has provided a constant view of the Sun at many wavelengths since its launch. Besides its direct solar observation, SOHO has enabled the discovery of a large number of comets, mostly tiny sun-grazing comets that incinerate as they pass the Sun. All these satellites have observed the Sun from the plane of the ecliptic, and so have only observed its equatorial regions in detail. The Ulysses probe was launched in 1990 to study the Sun's polar regions. It first traveled to Jupiter to slingshot into an orbit that would take it far above the plane of the ecliptic. And once Ulysses was in its scheduled orbit, it began observing the solar wind and magnetic field strength at high solar latitudes, finding that the solar wind from high latitudes was moving at about 750 kilometers a second, which was slower than expected, apparently. And that there were large magnetic waves emerging from high latitudes that scattered galactic cosmic rays. And cosmic rays are high-energy particles coming from everywhere in the universe. And no one really knows. I mean, there are a lot of different types of cosmic rays and a lot of different types of particles, and with many, many different sources. And the elemental abundance in the photosphere of the Sun are well known from spectroscopic studies, but the composition of the interior of the Sun is more poorly understood. A solar wind sample return mission, Genesis, was designed to allow astronomers to directly measure the composition of solar material, and that is just mind-boggling if you really think about it, that we are currently thinking about grabbing actual mass from the Sun and bring it back to the Earth, and that without having the satellites being incinerated like those poor comets. Well, we've got the Solar Terrestrial Relations Observatory, or STEREO. That mission was launched in October of 2006, and 2 identical spacecraft were launched into orbits that caused them to respectively pull further ahead of and fall gradually behind Earth. This enables stereoscopic imaging of the Sun and solar phenomena, such as the coronal mass ejections that we mentioned earlier. The Indian Space Research Organization has scheduled the launch of a 100-kilogram satellite named Aditya, after the sun goddess, or god, or deity, hoping for mid-2020s. Its main instrument will be a coronagraph for studying the dynamics of the solar corona. So we have an exciting future ahead of us when we'll find out more about the Sun. But currently we've still got a lot of information, and some observation data includes, of course, the distance, which I mentioned earlier, 1 astronomical unit, or 150 million kilometers, be with 8 minutes 20 seconds at light speed. Its visual brightness is negative 26.74, and the more negative the number, the more bright it is for astronomers. And its absolute magnitude is 4.83, which is the magnitude when you normalize the luminosities and set them at a theoretical same distance away from an observer. And its spectral classification is G2V, and its metallicity is 0.0122. Its angular size is 31.6 to 32.7 minutes of arc in the sky, and its orbital characteristics in relation to the galaxy, it's about 27,000 light years away from the core, and a galactic period, which is a galactic year, is about 250 million years, and its velocity, it's approximately 220 kilometers a second in its orbit around the Milky Way, and 20 kilometers a second relative to other stars in our stellar neighborhood, and about 370 kilometers a second relative to the cosmic microwave background, the oldest light that we can detect. And the physical characteristics of the sun, its radius, like we said earlier, is 109 times that of Earth, which gives it about 600 or 700,000 kilometers, and that's quite the distance. And its equatorial distance is about 4 million kilometers, and that is its circumference, which is also about 109 times that of Earth, and it's flattening at 9 times 10 to the negative 6 power, and its surface area is about 6.09 times 10 to the 12th power kilometers, and that is to say about 12,000 times that of the surface area of Earth, and its volume is 1.41 times the 10 to the 18th power kilometers cubed, which is to say about 1.3 million Earths. Its mass is about 1.9885 times 10 to the 30th power kilograms, which is about 333,000 Earths. And its average density is about 1.408 grams per cubic centimeters, and that is about 0.255 times the Earth. So it's less dense than the Earth, which isn't strange. It's not really a solid. It's mostly plasma, which is the state above gas in matter. And of course, the density at the core is much greater. We talked about that earlier. And the surface gravity at the equator is about 274 meters per second, and that means it's about 28 times that of Earth. So if you would stand on top of the surface of the sun, and you manage not to be incinerated, you would feel about 28 times heavier than you do here on Earth. And the escape velocity from the sun is 617.7 kilometers a second, which is about 55 times that of Earth at 11 kilometers a second. And its temperature varies, of course, depending on where you are at the sun. At the surface, it's about 5,000 or 6,000 degrees. But at the corona, which is a bit above that, you get 1,000 times stronger. You get about 5 million degrees, and at the center, like we said earlier, you have this insanely high temperature of 1.56 times the 10 to the 7th Kelvin. And its luminosity is 3.828 times 10 to the 26 watts. And that's about 3.75 times 10 to the 28th lumens, which gives its efficiency of 98 lumens per watts. And its age, like we said, is 4.6 billion years. Its rotation characteristics, we have the obliquity at 7.25 degrees to the ecliptic to us, and 68.23 degrees to the galactic plane. So if we would consider the solar North Pole to be up, if we looked at it, wouldn't be directly up the plane of the galaxy. It would be at a slight angle, or at a strong angle, actually. Its right ascension of North Pole is 286.13 degrees, 19 hours, 4 minutes and 30 seconds, and the declination of the North Pole is plus 63.87 degrees, 63 degrees and 52 arc degrees north. I'm not sure what that symbol is. Its sidereal rotation period at the equator is about 25.05 days, so it takes about a month for the sun to have its own day. And if we take a quick look at the structure of the sun, we have from the middle, we start with the core, the innermost 20 to 25% of the sun's radius, as we discussed earlier, where the temperature and pressure are sufficient for nuclear fusion to occur. Hydrogen fuses into helium, and helium cannot currently be fused at this point in the sun's life. And the fusion process releases energy, and the helium gradually accumulates to form an inner core of helium within the core itself. And moving away from the core, we have the radiative zone, and here convection cannot occur until much nearer the surface of the sun, and therefore between about 20 to 25% of the radius and 70% of the radius, there is a radiative zone in which energy transfers occurs by means of radiations, that is light, photons, rather than by convection, which is heat transfers from the hydrogen, the mass, I would presume then. And after the radiative zone, we have the tachocline, the boundary region between the radiative and convective zones. And then we get to the convective zone, between about 70% of the sun's radius and a point close to the visible surface. The sun is cool and diffuse enough for convection to occur, and this becomes the primary means of outward heat transfer, similar to weather cells, which forms in the Earth's atmosphere. And then we have the photosphere, the deepest part of the sun, which we can directly observe with visible light. Because the sun is a gaseous object, it does not have a clearly defined surface. Its visible parts are usually divided into a photosphere and a atmosphere. And then we get to the outer part, the atmosphere of the sun, a gaseous halo surrounding the sun, comprising the chromosphere, solar transition region, the corona, and the heliosphere. These can be seen when the main part of the sun is hidden, for example, during a solar eclipse. And now we're approaching the end of the episode, and if you haven't fallen asleep yet, that's okay. But since this is the very first episode, I don't have any more material to offer, so like I mentioned earlier in the description, you will find links to Scooter's podcast, Sleep With Me podcast, or you can go to sleepwithmepodcast.com and find more material for helping you fall asleep. And I don't think this will be the only episode in which I talk about the sun. There is a lot of things that I did not mention, such as sunspots and more cultural relations that we have to the sun, and its relation to the other stars in the stellar neighborhood, and probably a lot more. So I will not get tired of talking about the sun, but I'm thinking that the next episode I'm gonna go in the planetary directions and talk them in order. So beginning with Mercury, the closest planets, and the subsequent episodes will be about Venus, maybe Earth, since it is the third planet from the sun, but maybe I'll skip that and go directly to Mars, and then Jupiter, and Saturn, and Uranus, and last but not least, Neptune, since Pluto is not categorized as a planet anymore. But I will definitely talk about Pluto, since a lot of new discoveries has been made in the last years, and still being analyzed. And after the solar system, we have to think about what to talk next. And since it's the universe, it's supposedly endless, but we've got our neighborhood stars, and we've got our galaxy and our neighbor galaxies, and all the different phenomenons that occur inside them, and we got the black holes to talk about. So there will be a lot of subjects that will help you to fall asleep. But this is it for this episode. I'm hoping that you're asleep now. And if you're not, go into the description and see if Scooter can help you with his podcast, Sleep With Me podcast. But for now, I'm gonna say thank you for listening, and sleep well. And I hope you enjoy this and had use of this podcast. This is Felix signing out.